Hi, in this lecture, I'm going to talk about image enhancement. It will be a series of videos, and in this first video, I'm going to give you an introduction about this subject and also talk about point operations, which are often also called pointwise or pixelwise operations. Image enhancement is about modifying pixel values for better visualization. So we are going to try to obtain images that are better perceived by the human visual system, so by us humans. But those images that are better, then they can also be used as input to other algorithms. So the idea is that if we improve the quality of the image, we not only be able to perceive better objects and contrasts, but also can try to observe some particular features of the image that are harder to see in their original form or their original values. But before going into detail about the technique of image enhancement, I'm going to talk about a little bit of the definitions. The first definition is the intensity transformation. In this lecture here, everything that I'm going to explain is in gray levels. So we are assuming that the image has only 8 bits per pixel values, so values between 0 and 255. So when we talk about intensity transformation in gray levels, this is an alteration in the gray level intensity of individual pixels. We are operating pixel-wise, we're operating per pixel transformations. So let Z be the intensity of a pixel, a given pixel, and T a function that transforms this intensity. Then we have this basic equation, S equals to T of Z, where S is the value after transformation. Those, in the slides, those are 3 examples of functions that can be designed for specific purposes. The first one, on the left-hand side, is the identity transformation. The identity transformation doesn't change the image. It just keeps everything as it is. In the second one in the middle, we have the negative or inversion of the pixels, of the pixel levels. And finally, on the right-hand side, we have the contrast modulation, which will try to improve the contrast of the image by making dark pixels darker, even darker, and bright pixels even brighter. When we operate not only in every pixel or pixel-wise, but we also use other pixels, neighboring pixels, to perform some kind of enhancement or any kind of image processing operation, we call that space domain filtering. Those are used as input not only a value of a given pixel, but the actual image and their coordinates. So we often have this formulation, so g of x and y can be computed from the transformation of a function x and y. So we have both the value of the function and also the coordinates to work with. In this way, the transformation can consider either the pixel value, that is the neighbor is 1 by 1, so just considering the given pixel, the central pixel, but also some arbitrary neighborhood. And then we talk about neighbors. So if I have a given pixel at some coordinate x and y, it has 4 neighbors in horizontal and vertical directions. This is the definition of neighborhood that's more often used in the literature of image processing. I'm going to stop this presentation just to show you how it behaves in terms of coordinates. So often what we have when we talk about images is a function f of x and y. So this function in mathematics we often depict it or illustrate it in a plot as I'm showing you here. So just as this one. So we have the x in here and the y in this axis. So x is in the horizontal axis and y is in the vertical axis. So this is how we represent a function in this space. And f applied to x and y would be a third dimension here that will define how many intensity levels that we have. So let me just change here. So it would be as if I had a third axis here, and this third axis defines the intensity level of each coordinate. However, because we store images in the computer, and it's much more easier to work with those images as matrices, so modeling those as matrices, what we do is that we rotate this axis in order to do it like that. So this is what we call the rotated coordinates. So in fact, what we often have is the x in this direction and the y coordinate in this direction. This makes it easier for us to model the image as a matrix, so as this one. Starting is a discrete grid of values, of coordinates. So we have in the rows of the matrix, we have the x coordinates, and in the columns of the matrix, we have the y coordinates. And then for each pair of these coordinates, we can have a value that is coded using a specific number of bits codification. As we talked about in the last lecture, we often used 8-bit codification. This means that every pixel in this grid will have a minimum value of 0 and a maximum value of 255, because since we have 2 to the power of 8, then we have at most 256 values. So we can have an image with, I'm just writing here arbitrary values. I'm going to show you in a bit. So we can have something like this. So in the coordinate 1, 1, the intensity value is 0. In the coordinate 1, 2, the value of the pixel or the intensity value is 100, and so on and so forth. So we have this type of representation for images. So remembering that it is as if we rotated the plane in order to obtain a matrix or something that's similar to a matrix representation. That will define the neighborhood of a given pixel. So I'm just going to present change for the presentation again. So a pixel, any pixel P at some coordinate x and y have 4 neighbors in horizontal and vertical direction. This coordinate can be computed directly from the coordinates by summing or subtracting one from one of the coordinates, so either x or y. So those are the coordinates that correspond to the set of pixels that we call the 4 neighborhood of P, or N4 of P. We also can define the diagonal neighbors of a given pixel, and those diagonal neighbors can be obtained by summing or subtracting at the same time from x and y, and this set is often called ND of P. This is less common to use in practice. And finally, when we combine or we get the union between N4 and ND, we have all the 8 neighbors of P. This is considering that we have just a single, or a small, very small neighborhood region. So let's say we have an image as that. So we have here, again, this is those are the x coordinates and y coordinates. So let's say I have a pixel 5, 8, which means x equals to 5 and y equals to 8. What would be the neighborhood, the 4 neighborhood of this pixel P? So basically, what we have is, so I'm just highlighting here what's the pixel, so the pixel that I want. So a 4 neighborhood would include this pixel here, this one here, and this one here as well. So it is a kind of a cross neighborhood. So in this case, this set will include the 5, 7, 5, 9, 4, 8, and 6, 8. So this is a set of pixels that that correspond to the 4 neighbors of the pixel 5, 8. So this is how we define neighborhood in terms of image processing. So if you ever see some method that says that it operates on the 4 neighbors of every pixel, this is what the method means. So if it operates on all 8 neighbors of the pixel, then it includes all of them. So I'm going to just write it here. So so those are the N4, and when we include also all neighbors, we have the N8, or the all neighbors of a given pixel. Okay. So let's go back to the presentation. So given those basic definitions of images and how those images are interpreted in terms of the function and matrix, and as we see, we are going to talk about, sometimes we are going to talk about the image as a function of f of x and y, or other function g of x and y, and so on and so forth. But actually what we have is a matrix, and we can represent as a matrix. So how can we obtain image enhancement from such images? So we are going to codify this transformation by designing a function t and applying it pixel by pixel. An example of this function, of a transformation function, is the negative, or the inversion. Assuming that the maximum value of a pixel is 255, if I produce a transformation such as this, it will give me the inverted value of the pixel corresponding to the original pixel. Let me show you here that same plot that I showed you in the slide, and in a few slides previous to this one. So what we have is a function that operates on this type of on this plane. In this axis here, I have the input pixel, so a z pixel, ranging from 0 to 255. And in this axis, we have the output pixel, or S pixel, ranging also from 0 to 255. this is very important in image processing. When we are going to code some examples, you're going to see that in many cases, the more challenging aspect of coding image processing techniques is paying attention to the range of values that I'm working with. Okay, so we're going to talk about that later. So I draw here a function that is the identity function. That means when I have a 0 input pixel, the output is also 0. If I have a 63 as input, we also have a 63 as output. So I'm just going to draw here a small dot showing you that if I have this function, this transformation function, value of 63 maps to 63 on the output, so it doesn't change anything. So this is basically as if I had t of z equals to z. Right, this is just t of z equals z. So I don't change anything. What would be the plot that represents the inversion? So I'm going to draw here in a dashed line. So roughly, what you have is a line like that. So as you can see, the only case that it maps input pixel to the same output value is 127. Apart from that, everything else is inverted. So if I have the 63 value as input, that's going to map to 192. So a 63 as input will output 192. So a dark pixel, because 63 is closest to 0, then to 255, will become bright. And on the other hand, if I have a bright pixel, such as 192 or any other one, so this value is going to do the opposite. So 192 will be mapped to 63. So in this, this kind of plot here shows how the function behaves. So, and I can design different types of functions, remembering that those values, those lower values, are associated with darker shades of gray, while higher values closer to 255 are associated with brighter values. Okay, so let me choose the slide. Right. So another function that can be used is the contrast modulation. This is also called the contrast value adjustment. Is an enhancement method to stretch or shrink the range of intensities. This is performed by using a linear mapping between an input set of values. So when we say that the input image has pixels in between A and B, so the minimum is A, the maximum is B, we can map those into a linear vector from C to D. And this is the equation that's going to operate on the input value Z, and then output the new values for each pixel. So as you can see, those transformations or those functions, they operate on the intensity value of the pixel, and not in particular that coordinate. So it happens for for every pixel, for every intensity value, it behaves in the same way. We also have the logarithm function. It is very useful to shrink the dynamic range between the maximum and minimum intensities. So the log function is well known for saturating values when they go above some specific value. So it is used to change the dynamic range of the values between maximum and minimum intensities. And it has a specific shape. I think I'm going to show you in the code directly. And this shape of the function, we have to take care that also respects the range of values that we are interested in. To have an output value that is too low. So we want to keep the range between 0 and 255. That's why we have to multiply the log of a given z value with a constant c that is defined based on the maximum gray level in the image. We also have another operator called gamma adjustment that uses a power of a given gamma as a parameter in order to better adjust the values nonlinear. It is a nonlinear operator, so it can behave similar to the logarithm function, but with a different function. So when I change the gamma parameter, I can, for example, compute the square root of the pixel or the cubic root, or even a power that's higher than 1. So it will behave in a different way. So gamma is often defined something in between 0.05 and 1.25. So this are the most common parameters used in this case, but we can also define others. So let me stop right here and give you an example in the code. I'm going to stop the presentation to change the window to this, Okay, so this is the Jupyter notebook that we are going to use, and then I'm going to start by using here some image enhancement. In this case, image enhancement, it's basically point operators. Few examples. The complete notebook for this lecture will be available on a repository at GitHub.com, so you don't have to worry about it. I'm just implementing with you in order to exemplify what I mean. So I'm going to import NumPy, ImageAO, and Matplotlib. And then I'm going to show you that if I have a range of values, so let's say that I have different Z values. As I told you, the Z values are the intensity levels, so they range in the interval 0 to, so they have 256 different values. Let's print this array here. I'm going to give it so a little bit more space. So what I did here in Python was, in using the NumPy package, was to generate a vector of values ranging from 0 to 255. So in NumPy, it creates ranges in between some number and less than the number that are defined here. So let's say that I use 64, then it produces from 0 to 63 and so on and so forth. I can also use a pair of values. So if I use 10 to 64, it will create an array in between 10 and 63, so less than 64. Let me just go back to 256, which are the possible gray levels. Yeah. And then now I'm going to exemplify with some pixel-wise operations. So let's say that I want to produce the inverse, so the inverse of this of those values. So S as an inverted, it's going to be 255 minus Z. Let me, instead of printing it, I could print it as well. But it's also interesting to see. But instead of just printing, I'm going to plot it using the matplotlib library. I'm going to define the size of the figure. I'm going to choose here 8 by 8 just to make it easier for you to visualize. And I'm going to plot the input value Z against the inverted value. So as you can see, what we have is the same function that I showed you. So if I have, let's say, a value of 50, so if I use S invert and I inspect the 50 value, it will give me as output 205. If I wanted to know 63, so 192, and so on and so forth. But this is interesting because we can visualize it. But let us do that in an image. So I'm going to open using image.io, and I have a few images here for me to download. To load. And I'm going to also invert it. So in the inversion, this is the exact same operator that I use. So in Python, I don't have to go through in a loop, going through all values of the pixels. You may have seen it in a previous notebook that I asked you to run. So the same operation that I perform when I use the array of values, I can use on the input image. And I'm then going to plot it as well. Fixed size. A little bit larger this time. Then I'm going to show just the first image. What did I do? Oh, sorry, I used the wrong value. So this is the image that I'm going to work with. So in here, I just showed you the image one, so not the inverted version of it. I'm going to modify this code in order to show the two images side by side. In order to do that, I'm going to the function subplot. This function says that I have a panel with one row, two columns, And the next image I'm going to plot is the first position. So panel with one row, two columns, and show next image goes to first position. So if I just do that, it is going to show in the right hand, in the left hand side here. And I repeat that. I don't have to run it all the time. I just running it to show you. I could have run that once, just once. Now I showed both images at the same time. So the subplot function is very useful to do that. You may notice that I use this CMap equals to gray. This means color map. If I don't use that, Matplotlib will assume that the color map, so, the range of values it has to show is not gray, but another color map. In this case, it's in between yellow and green tones. So I don't want that. I just want the gray values to be interpreted as gray values. So I use color map equal to gray. So this is the E version. I'm also going to show you the logarithm. So the log version, if I want to compute the log of 2 of our Z array, I can just compute Z plus 1. This plus 1 is required because I don't want to try to compute Z equal to 0. So that's it. I forgot to plot it. So let's say 6 by 6. So the log behaves like that. So it has a saturating property. So the first values grow very fast, and then suddenly it starts to saturate. But look at the output values. So the input values are in between 0 and 255, but the output values are pretty low. So the maximum, if I try to find the maximum here, so np.max of z log 2, this is a little bit over 5, so very dark in terms of image. So I want that the maximum value, to be 255, such as the input value. So this is why we use that scaling factor. Let's say the scale, C scale, is 255, so this is the maximum value that I want to achieve. Let me compute again. Sorry. So 255 is the maximum value. I divide it by the log of maximum value, so 256 values. Now I compute the logarithm again, but now scaling it using this constant. And I'm going to show it again. Let me just copy that from above. Now the curve is as we wanted it to be. So the input value in between 0 and 255, and the output as well. So let us do that now in an image. So let me open another image. JPEG. Now I'm going to use the same function, the same log function, but instead of applying it on the array Z, we are going to apply it in the array EMG2. Then let us plot it Let me copy the one from above so we don't lose time. The same idea. I have to define the figure size and then subplot. So the first one will be image 1 and the second one log of 2 of that is the same image. It returned me some error. Let's see. See what I did wrong here. Okay. So this is the issue when we have implement everything all together. So let's make sure that it is loading. Yeah, it is loading. Okay. Okay. Now this is the first issue that I talked about a little bit before. When we work with images, the first thing we have to make sure is that the values are in the correct range. So when we apply the log of 2 of an image, the type of that array, of the image 2 array, this array has a specific type. And this type is the unsigned int of 8 bits. So we don't want that. If you compute the logarithm with that, it will probably give me wrong s. So I'm going to convert this. I'm going to convert the value, the input values, to another type. So I'm going to interpret the image 2 as a type of a NumPy type, integer 32. So it's basically a regular 4 bytes, 32 byte or 4 byte integer. All right, so now it is fine, but afterwards, it worked here fine, but then in order to be sure that the output is also correct, I'm also going to convert the type to unsigned int 8. So let's say here, so the input is unsigned int of 8. So in order to process, we convert it to to a type that suits the processing. So for example, it could be int 32, or we can also use float 32 or anything that we want. And then after processing, convert it back to signed int 8. That's what I just did here. So as we can see, the logarithm function increases or make the dark values. So in the regions that the image has very dark values, it became brighter. But the bright values didn't change that much. So this is how the log function operates. And as a final example here, more examples you can see in the notebook at the GitHub website. I'm going to show you the logistic function. So another function that can be interesting to look at is the logistic function. The gamma is also very interesting, but the logistic is, it has an S shape of the curve. So because it has this S shape, let me show you in a few, in this, draw it for you to see. The S shape of the curve will make we'll have this type of behavior here. So the idea is that dark values, I have a whole range here of dark values, and I'm going to compress this. So dark values become even darker. And for bright values, this happens similarly. So in the bright direction. So bright values become even brighter. So this improves the contrast of the image.